Okay, going to start a new problem. It's in route 13 again, so we're going to go ahead and convert that into something readable. So, given the root node of a directed graph, clone this graph by creating its deep copy such that the clone graph has the same vertices and edges as the original graph. Okay, and test it. So, I believe a directed graph is when, as opposed to an undirected graph where it goes both ways, a directed graph goes and is connected to one other thing, something like that. I'm going to confirm. So, yep, that is exactly right. So now we want to, I guess, take a root node, which I suppose means if we sort of branch out from there, then we'll definitely hit all the other nodes. And then we want to create a deep copy of that. So why don't we start off and just make a test for that? So we can say that, or I guess we can start off and make our file structure actually. So we can call this like copygraph.test.js, and also copygraph.js. So in our test, we'll start off and we'll make a graph and see what we think it should be, and then test that. So first we're going to have to require our actual function that we're going to be testing. So that'll be require copygraph. We also need assert, so that would be chai.assert. And as for our test, so this will be describing copygraph.js. And copygraph. And it should make a deep copy of a graph. We're missing the trick. So first we're going to make a graph, pass in the root node to copygraph, copy it, then we'll test and see if that is actually the same thing. So we can make our root node, and that'll look something like the value 7 and edges, I suppose. And this will direct it at some other nodes, which I'll go ahead and write above in just a minute. So I'll say it goes to node 1 and node 2. And I will need to make these as well. And these will both direct at, I guess, we'll say they both direct at a single node to make sure that we don't get any duplicates. And that is where it ends. So now that we have our graph, if we call copygraph on our graph or our root node, and if we check to see if the graph is deeply equal, so we can say assert.deep equal root copy and root. So that'll look and make sure that the roots are the same, and then it'll go through all the edges, and then so I think that will work as our test. We can go ahead and try that, make sure it at least runs. Copygraph is a function, it's not yet, so yeah, that's cool. So here, I guess at the very end we're going to say, we're going to export, we'll call it copygraph. So we want to make sure that we're not copying the same node twice. So I think first we can go ahead and say that we need like a function. That returns some copy of that node. The reason I'm declaring it inside is because I, construct that will allow me to make sure I'm not copying nodes multiple times. So if I can go ahead and say, make some sort of memory, and that equal to an empty array, and as we build nodes, we'll like push things into here, and keep track of it that way. Also, we'll, so I remember when doing like a depth first search for a tree, that a valuable way to keep track of the children was to push them into a stack. I'm going to be doing the same sort of thing here. So I think we can go ahead and say that the check nodes, or not the check nodes, so vertices to copy, and we'll set that, and at first we're just going to be doing root node, so we can initialize it that way. So I'm thinking in the memory, we can store it as arrays with maybe the first node equal to the original node, and the copy node, so that when we're going through, we can just check and see if it's already been copied. So if we continue on like that, and we just keep pushing in the children into the memory, and then we can say while vertices to copy dot length. So once I hit 0, it'll stop, and then we can return it a little yellow here. Yellow, not defined, not defined. Define the range. Sure. So the real meat is happening inside of this copy node function. So why don't we copy node memory dot shift. So we'll be putting stuff onto the, wait, not memory, vertices to copy. So we'll be putting stuff onto the back end of vertices to copy, and we'll be pushing, we'll be taking stuff off the front. So it's basically a queue on a stack. Yeah. So what do we want to do inside of copy node? First, we want to check if already we can say, if already in memory, return that value, or return copy from memory. Else, what we want to do is, so we want to make a new object with that value. We want to make a new object with that value. How did I make this again? Value and edges. And then you want to iterate through the edges and push in the same order to the edges array. The copy of all of the edges. Yeah. So I think that'll work. So we are going to make a new copy, or make a new object with the correct value, and for each child, or I'll call it child, it's an edge, push to push to edge array copy node of that edge. And at the very end, so we've made our edge, or our node at that point. So what we have to do is update our memory so that we don't do it again at some point in the future. So we can do memory, so actually stick to pseudocode, and we can say memory the original and the copy. Awesome, that'll work. So I guess we'll build out this first top part because that's easy enough. So if memory.find where, is that the new function? Find JavaScript. Okay. So if memory.find, let's see. we're putting the original node first. So find so for each pair, return pair of 0 equals node. Equals if memory copy, return memory copy. Let's go ahead and run through that logic. So we look through the memory and we check each pair. And if the first one, which is the original version, is the node we're trying to copy, then we return that copy. Makes sense. So we have a return, so we can go ahead and just build this part out here. Otherwise, we're going to make a new object with the correct value. So const node copy equals value node dot value and empty edges array. So then we need to iterate through all of the edges in the original node, and then push to the edge array the result of copying that node. So we can say for edge of node dot edges. And we can say node copy edges push. You want to push the result of copying that edge, right? So node dot edge. Wait, no. Copy node of edge. And then after that, we've built up our node copy. We can just return it. Yeah. So that's our function. We have our memory. We're just used to copy. And at the very end, we have to return something, right? So we can return very similar to what we just did. So we can say memory dot find, and we want to find the one that is the copy of the root node, right? So we'll return the second index. Did I ever actually push? No, I didn't push yet. So let's assume that this memory is built, and we'll go ahead and finish this part. So we can say for each pair, we want to return the one where pair of 0 equals and we'll return the first one where that condition is satisfied, right? So again, we have successfully built our node, but we are not pushing it yet to our memory, so we have to take care of that. So before we return our node copy, we can go ahead and push to memory. So we can say memory dot push a new array with the node and the node copy. Not seeing any yellow. I think that'll work. Let's go ahead and run our test, see if we got it. So, see what our test says. We'll make this a bit bigger. value to edges So, going to go back and look at the test and see exactly what we're comparing. So the first one is the copy, and the second one is the original, right? So again, what does our test say? Value 2. Having a difficulty reading exactly what this test is trying to communicate. It's not showing the entirety of the actual string, right? So I'm going to go ahead and comment this out. Maybe I can get a little bit more information from this. And I can just say, return, instead of node itself, I can return the memory. So we have 4 nodes inside of our memory. That looks fine. But it's not being equal to the value. So I'm going to go ahead and take one quick more pass at exactly what this is doing so we can sort of figure this out. So we initialize our memory. We say that the vertices to copy is just the root node. Is this even doing anything? Suppose it isn't, is it? Because we're just going to be calling this on the root node, right? So, I mean, this really simplifies to copy node of the root node. So that simplifies it a little bit, and it should simplify the analysis of this code. So what it says is copy node takes a node, and it says, okay, find inside of the memory where the first element of the pair will, and if that is a thing, then return. That makes sense. Otherwise, so we are going to make a new node called node copy, and that will have the original node's value and an empty array of edges. And we iterate through each edge of the node we're trying to copy's edges. And we say, okay, push to node copy. Push to the node copy edges, the result of copying the edge. And then, once that's finished, once all of those are finished, push to the memory an array with the node and the node copy. Then at the very end, we want to copy over. the very end, yeah, we just return the node copy. That makes sense. And then we export it. So let's see again. What is our test telling us? Oh, I'm returning the wrong thing still. We want to return the root node. Oh, suddenly it works. That's funny. I don't know what I changed, but it works. Hooray. Awesome. I'm going to go ahead and clean up some of the pseudocode because, yeah, I'm going to clean up some of the pseudocode and I'm going to see if there's anywhere that I'm not exactly happy with. So I got rid of that sort of useless stack that I had going. Let's see. So this operates in, let's see, as far as time complexity, what are we doing? So we definitely have to go through, if there are n nodes, we have to go through all n nodes. So let's just say we have a 1, and that goes to a 2, that goes to a 3, and then also we can say that the 3 goes to, oh, just right. The 3 goes back to the 2. So how does that work? We say, okay, first make node, also make the 2 and 3 nodes, and the 3 then comes back around to 2. So that will, in that case, I mean, that's a constant time operation, but if there were to be multiple of those, how would that work? I mean, I guess the real condition and where you would actually be looping over, looping back over nodes that you've already made is when you have multiple edges going to them. So it's hypothetically possible. I mean, if it's directed graph, it can go either way, like just one way or one way and back, right? So that would mean that you would potentially be making each and then looking back at each multiple times. So that's linear with respect to the number of nodes, but also, that again, linear with respect to the number of connections. So I suppose that's worst case in the square, but different things are happening. So it's kind of a strange sort of case. As far as memory complexity, making a copy for each. So that's definitely going to happen. We're storing them inside of a memory array, but there's not much overhead as far as actually just storing them in the array is concerned. Yeah, overall, I'm pretty happy with this solution. I think the code's pretty clean. It's really happy with my naming of variables, which I've been having issues with lately. Overall, yeah, I think this is workable.